Okay, so we're going to start some pretty exciting stuff this week. We're going to be looking at first order differential equations. Now, um, first order differential equations are harder. What we're going to be looking at, I think they're a little bit more challenging to analyze than the second order equations that we've looked at. So I guess maybe first let me explain why I'm calling it first for second order. If you remember all of the equations that we've studied so far, the diffusion equation was first order in time and second order in space. Laplace was second order in space, two spatial second order derivatives, and the wave equation was second order in space and also second order in time. So everything we've studied so far has been a second order differential equation, meaning there's at least one second derivative. We're going to study first order differential equations, and there's only going to be first order derivatives. It's going to be first order in the t variable, first order in the space variable. And we're always going to use t and x as our variables just because I want to keep things consistent, but there are plenty of first order equations that only involve spatial variables as well. So like first order in space, in the x variable and the y variable. Okay, and maybe we'll look at some of those next week. But for now, for this week, we're just going to look at time and space. We're going to look at t variable and x variable. Just keep in mind sometimes that t variable means time and sometimes it means space. But for the analysis of the equation, it doesn't really matter. Because we are going to be looking at more general first order equations. So we're going to start with linear differential equations, move on to something called quasi-linear differential equation, and spend just a little bit of time in fully nonlinear differential equations. Because we're looking in more generality, we're going to have more complicated solutions, and the technique is a little more complicated. It's more geometric, a little more complicated, a little different than the way you've probably analyzed differential equations so far. Another thing that I'll point out is you might remember in the equations we've looked at so far, there's been no coefficients on the derivatives that weren't constant. In other words, we've never looked at an equation that's like t times the partial derivative of u plus the second partial derivative of x equals whatever. Okay, it's always been, if there's any coefficients on those derivatives, it's always been a constant. Well, not so anymore. Even for linear first order differential equations, we're going to look at what happens if we have coefficient functions on those derivatives. And we'll look at non-homogeneous and all of these other things as well. And this is very analogous to what you did in the ordinary differential equations class. In your ordinary differential equations class, you are able to completely solve and study first order linear differential equations, not just linear differential equations with constant coefficients, not just homogeneous differential equations, but the full body of first order linear differential equations. You can write down the solution. The most common method, the way it's taught, is by integrating factors, but you can also do other things as well. You can also take a sort of variation of parameters approach. I don't want to get too far into that, but I just want to point out that this is very analogous to what you saw with first order differential equations in your ordinary differential equations class, whereas when you studied second order differential equations, you were really constrained to studying second order differential equations that had constant coefficients or that had a very specific form, or that you could there was something else that you could do, right? But in general, you did not solve completely second order differential equations like you did with first order differential equations. We're going to have something similar here. We're going to be studying, first order linear differential equations in the fullest extent possible. There's more subtleties than there are with first order ordinary differential equations, but that's just, you probably expect something like that. So I will be posting videos today. I'm going to post a video from a few semesters ago where I sort of derived the transport equation, which is a very common and ubiquitous, that's the word I was looking for, ubiquitous first order differential equation that's going to be very similar to the derivations that we've seen so far. But that's just to give you an example of where these first order equations come from. But first order equations arise from a number of different physical situations. And so anyways, we're going to be studying that. Like I said, it's going to be challenging, but I think you'll like it. Once I get kind of the couple videos with the basic theory going, we're just going to work through a whole bunch of problems kind of in increasing difficulty. And I think once we get through that, you'll have a pretty solid foundation for first order differential equations, first order linear differential equations. Next week, we're going to get into quasi-linear differential equations, and that just kind of cranks up the difficulty even more, and you'll see a lot of stuff there that you probably have never seen before. And so I hope it will be challenging, but I also hope that it will be interesting for you. And by the way, I know there's a ton of people in this class who have all sorts of different experience kind of applying math in their lives, in ways in their careers and stuff, in ways that I haven't. So please continue to talk about that in the discussions, especially if some of the stuff we're talking about intersects more with the stuff you're familiar with and can sort of offer a perspective that I don't have. I'm like, hey, this is how we use this, and that sort of thing. I've really enjoyed looking at the discussion posts. Okay, that's it.